Well, hello again. This is Chemistry B. We are on Unit 8, talking about redox reactions and equilibrium. Let's talk about rates of reaction, and this is day 1. So let's get started. Let's talk about what the speed of chemical reactions are. They can vary from very fast, instantaneous, to very slow. So the speed of a chemical reaction can be very fast to very slow. Examples of this which makes some sense to you. Striking a match. When you strike a match, it is a quick reaction, quick chemical reaction. But when you compare it to plants dying and being converted into coal, you know that that takes a long time. So quick to very slow. All right. In chemistry, we say that the rate of a reaction is how fast the change occurs in a given time. And this chemical change, or the reaction rate, is expressed as the amount of reactant which is changing per unit of time. Rates of reaction are related to the properties of the atoms, the ions, and the molecules. So what causes them to be fast or causes them to be slow is related to the properties of those atoms that are involved in the reaction, which should make some sense. Now, we have this idea, and it's called the collision theory. And the collision theory is a model which explains how atoms, ions, and molecules can react to form products when they collide with one another. All right, let's take a look at this picture that we have right here. We have NO and O3, all right? And you see a picture at the top part of the picture is an ineffective collision. And at the bottom half of that picture, you see an effective collision. There are a couple factors which determine whether it's going to become an ineffective collision or an effective collision. If the colliding particles have enough kinetic energy and collide at the right orientation or angle, then they can react to form a new product. All right? This would be an effective collision. So if you see NO plus O3 at the bottom, the NO is moving with enough kinetic energy and at the right orientation, and it knocks into the O3 and it causes a reaction. And you see what happens here. It produces NO2 plus O2. So what has happened? One of the oxygens from the O3 has attached itself to the NO, and now we have NO2 plus O2. All right? If the collision does not happen with enough kinetic energy or at the right orientation, then no reaction takes place and the reactants bounce apart unchanged, as you can see at the top. So this is the collision theory. Two ideas that you have to keep in mind. Enough kinetic energy and the right orientation will cause an effective collision. If there is no reaction when you place two things together, it's because they do not have the right kinetic energy or orientation of the particles to make a reaction. Okay? Now, the minimum energy that colliding particles must have in order to react is called activation energy. In other words, it's a barrier that reactants must overcome to become products. Take a look at the picture. We have CO2 plus NO. All right? And they are the reactants. And as you can see, when they collide, energy is created. And as the energy increases, we get to the activated complex. And at the activated complex, that is where the reaction starts to take place. That is the peak of the activation energy barrier. The unstable arrangement of the atoms takes place. In other words, the breaking apart of the CO2 and the NO. And this is where products are started to form. And as you can tell there toward the right side of the picture, we have one of the oxygens has broken off of the CO2, and it has joined the NO, and we now have CO plus NO2, and those are the products. So if you're looking at this diagram, if the CO2 and the NO collide, but they don't collide at the right angle or with the right amount of energy, then they will not get over the barrier. They will not reach the activated complex area because they don't have the force or the orientation necessary for that to take place. If there is a reaction takes place, then you understand that the reactants had enough of the kinetic energy to overcome the activation energy barrier. All right. What affects these reaction rates? Number one, temperature. Generally, raising the temperature will speed up the reactions. Why? Well, you know this. Increased collisions and chaotic movement, as well as more particles with enough kinetic energy, causes the products to form faster. If they're moving faster, they're going to cause more chaos, more movement, more collisions, and that will allow them to form faster. For example, if you have charcoal that's in a bag, it won't burn. You light it on fire, increasing the temperature, that sucker burns. Number two factor for affecting reaction rates, concentration. In other words, the number of particles in a given volume affects the rate at which reactions occur. Of course it does. Cramming more particles into a fixed volume increases the frequency of collision, therefore leading to a higher reaction rate. All right? And finally, particle size. The total surface area of a solid or liquid reactant affects the reaction rate. Why? Increases in the surface area increases the amount of the reactant exposed for the reaction, which increases the collision frequency and the reaction rate. One of the examples that I like to use is NASCAR versus go-karts. Let's say you have NASCARs placed at the Daytona 500 racetrack. And they go around and around and around, and there are a lot of collisions that takes place. And as you know, that's really the only reason anybody watches NASCAR is to see the collisions. Okay? What if you put a smaller car on that track? Track is the same size. More area for those cars to move around. Do you think there will be more collisions or less collisions? Well, we're going to say that the speed stays the same, and we're going to say that the ability to control the car, even though it's smaller, is the same as the NASCAR car. Everything is the same except for the size. The width of the track is the same. Speed is the same. Well, of course you know what's going to happen. You know that there's going to be less collisions because the cars are smaller, because there's more room for the cars to maneuver around. So particle size does matter. All right? Factors. Let's go. Oh, here we go. Another factor that affects reaction rate are catalysts. Catalysts are substances that increase the rate of reaction without being used up in the reaction. Why is this? It permits reactions to take place in a lower energy path. In other words, they will lower the activation energy barrier, allowing more, sorry about that. Catalysts allow the activation energy barrier to be lowered, and that allows for more reactants, the ability to form. All right? Catalysts are shown above the arrow in a reaction equation. So in the arrow in the equation, you will see it. In our example, our enzymes in the digestive tract break down protein molecules, allowing digestion at a faster rate. All right? And that is all for today.